Hi friends, this is Rashekar, a GATE faculty for electrical machines. In this video, we are going to discuss about the previous GATE question. See a problem in this video. The percentage of impedance of a 100 kVA transformer. The percentage of impedance of a 100 kVA 11 kV by 400 volts delta star 50 Hz transformer. Nothing but the delta is 11 kV and star is a 400 volts is 4.5 percentage. The percentage impedance they given, that is 4.5 percentage. For the calculations of the load current, what they want? Of the load current during the short circuit test. Calculation of the load current during the short circuit test with LV side shorted. We know that in short circuit test LV is shorted. The applied voltage on the high voltage side will be applied voltage on the high voltage side will be, they are asking like that. What they given, sir? They given the percentage impedance is equals to 4.5 percentage and it is a 100 kVA transformer and 11,000 by 400 volts are the voltage rating. Nothing but this is my transformer. This is my transformer. 11 kV on primary side. 11 kV on primary side. 400 volts on secondary side. But this 400 volts is short circuited. And generally we are conducting the short circuit test. So on primary side we are applying the voltage. This is reduced voltage. According to given data, if you applied here 4.5% of rated voltage, then rated current or full load current flows in the transformer. But now they are asking of the load current. To get the of the load current, what is the applied voltage on HV side? To get the of the load current, what is the applied voltage on HV side? Let's do here to get the of the load current. To get the of the load current, applied voltage is equals to get the of the load current, applied voltage is equals to half of the 4.5% of 11 kV. Half of the 4.5% of 11 kV. Because if you apply 4.5 percentage full load, but to get half the full load, the voltage is equals to half of the 4.5% of the full load. Then these two zeros gets cancelled. 2 ones, 255. If you calculate this, the answer is 247.5 volts. If you apply 247.5 volts, then you can get the half the full load current. If you apply 4.5% full load current, if you apply 247.5 voltage here, then half the full load current flows in the transformer. This is the question. Very simple. They will ask you in question. This is the previous GATE question. Are you okay? The function of oil in a transformer is. What is the function of oil in our transformer? Generally, we have a transformer like this. In this transformer, we have a core, of course. This core is placed in transformer oil. Then what is the purpose of transformer oil? Generally, the purpose of transformer oil is the first one, cooling. This transformer oil flows through the cooling tubes or radiators, by utilizing the external air or atmospheric air, this transformer oil gets cooled down in the radiators. So the transformer oil is used for cooling purpose, to provide cooling, as well as the transformer oil having high dielectric strength and high insulating property. That's why it is also provides insulation to the transformer. So the transformer oil provides insulation as well as cooling. Both are correct answers. This is the function of transformer oil. Which type of transformer oil we are using in the transformer? They will ask you question. Generally, nowadays we are using mineral oils as a transformer oil. Mineral oils, or in some cases synthetic oils, are used as a transformer oil. They will ask you question. What is the trade name of transformer oil? What is the trade name of transformer oil? The trade name of transformer oil is Ascaral. Trade name of transformer oil is Ascaral. And what is the chemical name of transformer oil? The chemical name of transformer oil is pyroil. Pyroil or pyrochloroil. Pyrochloroil or pyrochloroil. You have to remember these things. Is it okay? Trade name and chemical name, and what is the function of transformer oil? Right. Auto transformer is used in transmission and distribution. Which of the following is correct answer? Like that. When we are using auto transformer in transmission and distribution. First one, when operator is not available. Is this correct answer? No sir, even for auto transformer also we need a operator. Next one, when iron losses are to be reduced. Of course, iron losses are less in auto transformer, but this is not 100% correct answer. And next one, when efficiency ignored. Why we have to ignore the efficiency? Efficiency is good in auto transformer, of course. So this is also not correct answer. Next, when the transformation ratio is small. Right, when the transformation ratio is small, then we have to use auto transformer. I said you the transformation ratio nearly equals to 1 only. For example, 100 by 1000 volts, then transformation ratio 1 by 10. This is not 10 by 1, because I said you LV by HV. Like that, the transformation ratio when nearly equals to 1, then only our auto transformers is preferable. I said you already. That's why the last one is the correct answer. When the transformation ratio is small, at that condition we can use auto transformer. Actually, they should give like a when the transformation ratio nearly equals to 1. But they given indirectly when the transformation ratio is small, also correct answer. This is the preferable correct answer for our question. Auto transformers are preferable when the transformation ratio is small. Are you okay? See this question. Keeping in view the requirement of parallel operation. Keeping in view the requirement of parallel operation, which of the three-phase connections given below are possible? For parallel operation, which of the following given connections are possible? They are asking like that. Here I said you, for parallel operation, the requirement is same phase group is one of the requirement for parallel operation. I said you delta delta and star star belongs to one phase group, and delta star and star delta belongs to one phase group. For parallel operation, the two transformers should belong to same phase group. This is the first condition. So see here delta delta and delta star, different phase groups. And here delta delta and star delta, different phase groups. And here star star and delta star, different phase groups. But here delta star and star delta, same phase group. So this is maybe correct answer. Sir, why this is not possible? Because this is 0 degrees and this is 30 degrees. So the phase displacement is around plus or minus 30 degrees. It should be 0. Here also this is 0 and this is plus or minus 30 degrees. So the answer is plus or minus 30 degrees. This is also not possible. Here this is 0 and this is plus or minus 30 degrees. Again the answer is plus or minus 30 degrees displacement. That is also not possible. But here for delta star plus or minus 30 degrees, for star delta plus or minus 30 degrees, it may be 0 also. If both are minus 30, 0. If both are plus 30, 0. So there is a possibility to get 0. So there is a possibility to parallel operate. Among all these, this is the more preferable parallel operation. This is very important for us. Is it okay? Right, sir. See this question. The low voltage winding of a 400 by 230 volts single phase 50 Hz transformer is to be connected to a 25 Hz. What happened, sir? Actually, a 400 by 230 volts 50 Hz transformer, this low voltage side connected to a 25 Hz. The supply voltage should be, what is the voltage of this one? They are asking question like that. If they ask you questions like this, here we have to maintain V by F ratio constant. V by F ratio constant. We have to maintain V by F ratio constant. Let's see, what is the first V by F? The first V by F is equals to 230 upon 50. What is the next V by F? We don't know the next V, but we know the frequency. This V by F ratio should be constant. Nothing but 230 by 50 is equals to V by 25. 230 by 50 is equals to V by 25. 25 ones, 25 twos are 2 ones, 2 115. So the supply voltage should be 115 volts. The supply voltage should be 115 volts. Like that, questions are important. They will ask you question. Actually, he has to mention here for same magnetic circuit, for same magnetic characteristics, for same magnetization current, for same magnetization current. Like that, they will mention you for same magnetic circuit, for same magnetization current, for same flux density, for same flux density, for same V by F ratio. They will mention you. If otherwise they mention, you have to consider V by F ratio constant. V by F ratio nothing but B maximum. B maximum constant or V by F constant or I mu constant. Magnetizing current constant, magnetizing component constant. Like that they will ask you in the question. For all the questions the answer is we have to maintain V by F constant. If V by F constant, then the voltage should be 115 volts. This is a question important for competitive exams, right? The law of electromagnetic induction, nothing but Faraday's and Lenz. Faraday's and Lenz are summarized in the following equation. The Faraday's law and Lenz law summarized in which of the following equation? In which of the following equation? According to Faraday's law, the EMF induced is directly proportional to rate of change of flux linkages. Rate of change of flux linkages. And according to Lenz's law, the EMF is opposes the rate of change of flux linkages. According to Lenz's law, EMF will opposes the rate of change of flux linkages. So finally, E is equals to minus d psi by dt is our answer. Yes or no? We already saw the basic principle. So this is wrong answer, this is wrong answer, and this is the correct answer. E is equals to minus d psi by dt. This minus given by the Lenz, minus given by the Lenz. This is given by the Faraday. This is given by the Faraday. This is the summarized equation. The basic principle of transformer equation, E, the statically induced EMF, is equals to minus d psi by dt. Of course, this is also can be written as minus d by dt of n phi. Flux linking nothing but n phi. So minus n into d phi by dt. I think this is well-known formula for you people. Right? This is our answer. So according to options, option C is correct answer. Don't take none. Sir, this is actually answer, so none of the above is correct answer. No, 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 sir. This is and this is both are same. Right? See this problem. This is very important problem on efficiency. The efficiency of a 100 kVA transformer is 0.98. For 100 kVA transformer, efficiency is 0.98 at full load as well as off load. The efficiency of the transformer is 98% at full load as well as at off load. For this transformer, full load copper losses are how the full load copper losses? Option A, the full load copper losses is less than core losses, equals to core losses, more than core losses, none of the above. Nothing but they are asking to get the same efficiency on full load and off load. What is the relation between copper losses and core losses? Equal, greater than, less than. Let's see how. So generally, they given 100 kVA transformer, full load efficiency 98%, off load efficiency also 98%. Like this they given. Can you tell me what is full load efficiency? Full load efficiency is equals to kVA into power factor. kVA, 100 kVA into power factor. What is the power factor? Power factor they won't mention, so unity. kVA into power factor by kVA into power factor, or here take kVA, that's why 100 into 1000 into power factor by 100 into 1000 into power factor plus iron losses plus copper losses. We don't know the iron losses and copper losses. This is efficiency at full load. And efficiency at off load is equals to half of the kVA into power factor by half of the kVA plus iron losses plus at off load Copper losses are half square of the full load copper loss. For these two, the efficiency is same 98%. So here the efficiency is 98%, and here also the efficiency is 98%. Now calculate them. We have to cross multiply them. 2 ones, 2 50s are. 2 ones, 2 50s are. 50,000, 50,000. 100,000, 100,000. Iron losses and copper losses. So do it. So 100,000 into 98. 98 into 100 into 1000 plus 98 into iron losses plus copper losses is equals to 100 into 100 into 1000. 100 into 100 into 1000. Right? We have to make it answer. So 98 into iron losses plus copper losses is equals to, bring this one to here. Here 98 into 100 into 1000. Here 100 into 100 into 1000. So take the common of 100 into 1000. 100 into 1000. So here 100 is there. Here 98 is there. 100 minus 98 is the 2. This is one equation. As usually here also take the equation. What is the equation here? 98 into 50 into 1000 plus 98 into iron losses plus 1/4 of copper losses is equals to 100 into 50 into 1000. What is the answer here? 98 into iron losses plus 1/4 of copper losses is equals to 1/4 of copper losses is equals to. Tell me, bring this one like this side. So same 50 into 1000 common and 100 minus 98 is equals to 2. We have to solve these two equations. Then you can get the answer directly. If you solve these two equations, you can get the answer. Copper losses is equals to 2 times of the iron losses. Copper losses is equals to 2 times of the iron losses. Nothing but the copper losses are more than the core losses. Copper losses are more than the core losses. Copper losses are more than the core losses is the correct answer. Sir, I have to take 1000 or not? If you won't take 1000, then the losses in terms of kilowatts. So no problem at all. If you want to take this 1000, this 100 into power factor, as well as 100 into power factor, as well as 100 into power factor, as well as 100 into power factor, you can do answer like this also. Then what is the answer? See, even though at this condition also 98 into 100 plus 98 of iron losses plus copper losses is equals to 100 into 100. Again, what is the answer? 98 of iron losses plus copper losses is equals to 100 common, so 200. 100 common, 100 minus 98, 200. As usually, what is the answer here? Same, 98 into iron losses plus 1/4 of copper losses is equals to here 50 is the common, not 100. Here 50 is the common, so 50 into 2 is equals to 100. If you solve these two also, you can get the answer. What is the answer? the copper losses is equals to 2 times of the iron losses. Copper losses is equals to 2 times of the iron losses. This is simply our question, which is very important for competitive exams. So here the copper losses are more than iron losses, then only for full load and off load we can get the 98% of efficiency. Are you okay? The magnetizing current in a transformer is rich in. This is the very important concept we discussed in three-phase transformers. For the wave shape of the EMF equation, to get the sinusoidal EMF equation, the magnetizing current should contain third harmonic currents. The magnetizing current should contain third harmonic currents. For example, this is normally three-phase, normal fundamental, but when we have a third harmonic components, then when we have a third harmonic components, then the waveform is like this, then the waveform is like this, which is called peaky waveform, which is called peaky waveform of magnetizing current. Then only the EMF is sinusoidal. So, in generally, in magnetizing current, the third harmonics are richest harmonics. The third harmonics are richest harmonics. We know harmonics nothing but the integer multiples of fundamental. Integer multiples of fundamental. Integer multiples of fundamentals are called. Integer multiples of fundamentals are called harmonics. Are called harmonics. Here even harmonics already eliminated. Remaining harmonics are triplen harmonics, fifth group harmonics and seventh group harmonics. In that the third group or triplen harmonics are richest in magnetizing current of transformer. This is very simple question, right? See this question. In a constant voltage transformer, nothing but CVT, constant voltage transformer, the output voltage remains constant. Yeah, that's why it is called constant voltage transformer. The output voltage remains constant due to, okay, why the output voltage is constant? They are asking question. Options: due to capacitor, due to input inductor, due to saturation, due to tapped winding. Due to tapped winding. Which of the following is correct answer? They are asking. Generally, in constant voltage transformer, even though the load changes, output voltage also changes, but to maintain constant voltage, we are using tappings on the secondary winding. We are using tappings on the secondary winding. By using these tappings, we can maintain constant output voltage. We can maintain constant output voltage. That is the reason here the output voltage is constant. These are the wrong answers. These are the wrong answers. Due to tapped winding only, here the output voltage is maintaining at constant levels. This is 100% correct answer for CVT, constant voltage transformer. Okay, very simple question. See this video. A different problem, different question. If an AC voltage wave is corrupted with an arbitrary number of harmonics, AC voltage wave is corrupted with an harmonics, then the overall voltage waveform differ from its fundamentals. Yes or no? Yeah, absolutely. This is differ from its fundamentals. Fundamental frequency component in terms of, so the difference in terms of course it is differs, but the difference in terms of, option A, only in peak values, option B, only in the RMS values, option C, only in the average values, Option D, all three measures nothing but maximum value, RMS value, average value. That is peak value, RMS value, average value. Now tell me which of the following is correct answer. This is a AC wave, right? So all three measures will changes when the harmonics are introduced. When the harmonics are introduced, all the three measures will change. No one is normal thing. So here the answer is all the three measures will changes. All the three measures will differ from its fundamental wave. This is the answer. Remember this question. Right? Thank you.